regarding is this tutorial lecture, I guess, for discrete mathematics. Today we're doing 1.3 propositional equivalences, which is what it means is when you have two propositions, are they equivalent or not? You can't say they're the same, because if you do equal, if I say P and Q is equal to, let's say, Q and P, this is not true. The reason is because equal means the same, like 2 equals 2, right? It means it's the same. But this obviously, like the outcome is the same, but they don't look the same, therefore they're not the same. They're equivalent. Okay? This lecture is going to be quick. It's not going to be too long. Okay, so tautology, I would say remember the words, but there's only 3 words, I believe. Tautology, contradiction, and contingency. Tautology is because it has a T, it's always true. That's how I remember it. A contradiction is always false, and you can remember that as you're contradicting yourself. Like you're saying something, you're saying it as if there's true or false. Like, is it raining? But right, like, is it raining is true or false, but it's always false. So like I'm contradicting myself. Contingency is basically just, it's either or. It can be true or false. Okay, so that's how I like to remember it. So consider the following compound propositions: P and not P. Basically what I'm saying is P, if this was true, and not P, which means it's false, this will be false. But if this was false, this would turn true, right? Because this is the opposite of this, so this will always return false, which is a contradiction. Here, this is always true, because if this is true, then this is false, and if this is false, then this is true, because this is nodding, right? But this is an or. Remember, an or says I only want one. Well, actually, it doesn't say I only want one. That's an XOR. I at least want one. And so this serves that purpose, is that it will at least always have one true. And so it will always be true. So it's a tautology. And this one, it's either or. So I have P and Q. Like when P is true, it doesn't depend on this. So this is, if this is true and this is true, that would be true. But if this was true and this was false, that would be false. And so as you can see, you could have multiple options, true or false. And so this is a contingency, which means you can have either or. 2 logical formulas are said to be logically equivalent, provided they have the same truth values under all assignments. Basically what they're saying is, if you do like a truth table of both sides, I'm not going to actually do a truth table because we did that last lecture, but if you do a truth table for this side and you do a truth table for this side, if this under all combinations of P and Q, like T T here, F, and then F, T, F, if after you run through these, they result in, let's say, like T, 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 and then you do the same thing here, and it gives you the same final solution, that means they're equivalent, right? And so there is one more way to prove it, and this is what we're going to go through in a bit, but I'll tap into it right now. You can use some De Morgan's law. De Morgan's law is basically saying if something is outside the bracket, you can put it in. Well, actually, this is like distribution law you can think about, but De Morgan kind of covers both of them. So you can distribute just like you do in math. And so you see, as you distribute, what this becomes is not P. This flips not Q. Equivalent. I haven't changed this. This is not P or not Q. And as you can see now, they're both the same, and I just proved they're equivalent. One more thing, do remember that this does flip. Whenever you distribute a negation, this will always flip. Don't ask me why. Go do a truth table and you'll find out that this, even though I just flipped it out of nowhere, is still equivalent to this. Or the truth table for this is still the same truth table for this. That's just De Morgan's law. Don't question it. Just know you gotta flip it when you negate. There's really not much to understand besides just doing that. You see, same thing here. If you expand it or if you do a truth table, you find out they are equivalent. So you'll have not P and not Q equivalent to not P and not Q. Jesus, I'm starving, bro. I've been yapping so much. Okay, so this is the table. I'll go quickly through each one to explain what it does. You see this T, this just says true. So P and true, it doesn't matter. So P and true says both of them have to be true to result in true. So we already know this is always true. So for this whole thing to give us false, we really only depend on P. Because if P is true, this will return true. And if P is false, this will return false. So we don't even need this part. We can just say P. Because now if P is true, it will return true. And if P is false, it will return false. And obviously the same thing here. This is for false though. Let's make this a little skinnier. I feel like that would be better. Okay. Domination just says it's basically the same thing as the one above it. Very similar. So you see here, I'm saying P or true. Now, or says at least one true, and so this will always be true because it says or true, and this will never change. This true will never change, and so this will always result in true. And this P and false, well, the end symbol, or what is it called? I forgot the name, but call it symbol, I guess. The symbol basically says I need both of them to be true, or both of them to be true to return true. And so since we know this is hard-coded as false, it doesn't matter what P is. This will always return false unless this returns true. Then P will matter. And so that's why this will always return false. Now for this, I'm saying basically P or P. So if P is true, this will result in true regardless of what this is, even if, like, you can't really make this false because this P is true, and this is the same P. So you see, this doesn't matter. Saying P and P, this is, again, true and true, or false and false. So the only thing that matters is P. Okay? So far, this is mostly common sense. Can't fucking spell. Community, something. Laws. You can read it, okay? P and Q is same as Q and P. Like saying you and me is the same as me and you. Well, actually, it's you and I and you. That sounds weird. Englishing. So same thing as P or Q or R. You can switch it up if you want. Doesn't really matter. Associativity laws. This one basically says if so what they're doing here is instead of having this together and R on the side, they just group these together and you can group it. It's like basically, if you think about it like multiplication wise, if I do, let's see, 1 times 2 times 3 is the same thing as if I did 1 times 2 times 3, right? So you can literally think about this law the same way. Is basically multiplying shit together. And it's the same with the OR. Okay? Distributivity law, that one is distribution. Again, it's a lot like math. It's just discrete English, but it's actually math. As you can see, for this part, they just distributed it. So when you have P and Q or R, and you just distribute, right? But what you have to do is flip the symbol in the middle, and then flip the symbol that you're distributing into. So since I'm distributing this in, they group like this. It becomes this, or, right, because I have an or this. Like, that's how they group. I feel like that's hard to see, so I'm going to write it out. So basically what they're saying is if I have P and, and Q or R is the same as if, let's group these two together, right? So we'll do P and Q. That's a horrible looking Q, right? And I'm saying or P and R. P and R. Right? So it's multiplication. You're just multiplying in the one under it. So by the way, you can go either way. Like if you see this, you can just pull out a P, or you can't pull out a Q because if you do it for one side, you can do it to the other side. But it's an R, so you can't really do that. Literally exactly like multiplication. Like if I had X times Y, let's see, plus z. Okay, so see I can multiply n and it will be x, y. Remember, you see the plus stays? Whatever the sign here distributes between these two, right? And so it's the same thing. Whatever the sign here distributes between these two, and then it also distributes between these two. So see xy plus, so sign in the middle, you see the sign in the middle here, stays the same, plus xz. These are the same. And so that's distributivity law, and you can go backwards. You can pull out an x, and you see, like, I'll pull out these two x's out. And so x times whatever stays here goes, and then y plus z. Literally same as multiplication. De Morgan's law basically says if you know something, like you can distribute it, but you have to flip the middle sign. That one, there isn't really much explanation to go into it. That's just like the rule is if you negate something, just flip the sign in the middle, and vice versa. You cannot, I've seen some people where, yeah, we'll leave it at that. I've seen some people that introduce a negation, like when they see a problem that's like P and Q, and they think one step they can do is introduce a negation. Like, hey, I'm going to use De Morgan law and introduce a negation. You can't do that. So De Morgan law just says if you do have a negation, you can apply it into it. And so it becomes not P or not Q. And as you can see, we always flip these. You can always also pull it out. So whatever is here, you can go this way or you can go that way. So it's not just one way. Absorption law basically says, what's the best way I can explain absorption law? I would say true or false. That's probably the best way. As you can see here, what I'm saying is P and P or Q. But here, let's assume P is true and Q is false. Okay, so P is true and Q is false. So this will turn into true, right? So that's our first side is right. This second side, what does it give? This is true and this is false. But since this is an OR, this will turn a true. So therefore, P is true and true. Okay, so now what if we flip it to false and true? As you can see, if this was false, right away, this end won't work because the end wants this to be true and this whole thing to be true, right? And so as you can see, this actually only depends on P because it doesn't matter what Q is, this only depends on P. And so that's why it only equals P, okay? And this is the same for the OR, but the like just OR and AND instead of AND and OR. And the negation law basically says, well, we learned that above. You're saying P or not P. You're basically saying true or not true, which is false. And if you say false, you're saying false or not false, which is true, which will always give you true. And this is the same thing we went over. Negating, so up here, I don't think I went over this. Double negation is P. It's just you're doing basically minus 2, which is just these cancel out, right? It becomes just a positive 2. So same thing. Now I have a couple formulas. I would say attempt to do these. Simplify it. I'll go through it. I've seen the lecture, the way he did it. I feel like it's one of the steps was a little bit harder, so I'm gonna show you the way I do it. If you don't like it, just follow the way he does it. I don't really understand the way he did it, so don't worry about. I'm not worried about how he did it. But anyways, this one, as we know, you can always distribute these in. The first thing you should do, actually, let me give you a little bit of advice. The first thing you should always do is look at the smallest version of it and be like, can I manipulate this in any way? No, the only thing you can do is not Q and not P, which is I just took this here and took that here. So that doesn't really do much. So you're like, okay, then can I introduce something else? Is there something near it that I can like use maybe? And see here we have a negation. So right away we're like, okay, well that's our only option. So let's do that. So you put it in, not P, and you put it in, lol. Okay, anyway, so it becomes like this. So now what you used De Morgan. You just want to write it like that. And then now you're using negation, which is not and not, is just cancels out. Same thing here, and this is just P and Q. Right? I hope you guys are finding it simple. Now this does look longer. It's not all that hard. Remember, first look at the smallest form. Can I do anything here? No. Can I do anything here? Still no. Well, can I do something here? No. Like you gotta just, it's like edge cases. Cancel out. Like know what you can do and what you can't. Okay. Now as a whole, what can I do to it? Can I distribute this here? No. Okay. Can I pull these out? Well, no, because they're not the same. Can I pull these out? Yes, they're the same. So that's the first thing we're gonna do. Let's pull out the P. So if we pull out the P, remember the and sign stays the same. Whatever is beside the P, whatever is beside what you're pulling out stays the same. Just like the XY example. And then these two will get grouped. Right? Because we pulled out the P, so these two will get grouped, and the OR will go between them. So it's Q or not Q. Okay? And so now where can we go from here? Again, you say, well, can I simplify this? No, you can't really do much there. Can I simplify this? Well, yes. Why? Because here you're saying Q or not Q. You're saying like true or, well, not true, which is false. Or you're saying false or not false, which is true. So this will always give you true. So therefore, this can simplify to just a T. Okay? So this will be P and T. And so you see it in one of them. This is the domination law. Actually, which one is this? When you turn this into P and not P. Sorry, I chose the wrong one, I'm pretty sure. Is it not here? Oh, there it is. Negation law. Whoops. Yeah, so we use here negation law. Well, here actually we used... I'm just bad with the names, to be honest. This is distributivity law right here. I'll just write distra. This one we use, as we see up here, we use negation law. So negation. And obviously if we're saying P and true, we know this is always true, but if this is true, this will become true. But if this is false, this will become false. So only really depends on P, right? And so the answer is only P. And this one I believe is the first one. Yeah, identity law. So this is identity. Okay. This one, a lot of people, I think that's where he had a long ass solution for it. I didn't even get it. So we're just gonna do the simple one. I'm not sure if he accepts it, but listen, it's the right answer. So if he doesn't do it, that's his problem. I'll probably argue him about it, like, yo, it's valid math, what are you talking about? Okay, so the first thing, again, can you do anything here? No. Can you do anything here? No. Can you do anything here? No. Okay, what about this part? Yes. So you just, that's basically how you do it. You just start small and go big. So the first thing is we're going to distribute this in. It's going to be not P. And we're going to flip the sign. Remember to flip the sign. Or not Q. Or not P and Q. Okay. So this is the first thing we use here is De Morgan. I wonder what De Morgan is. Okay. So again, here we'll use the negation just to cancel these out. Just because if you just look at it as a whole, there isn't much I can do or I can think of doing. This is the first step that comes to mind. Sometimes, I will say sometimes, just because you see this, do not get rid of it right away. And this is not, I'm not saying it specifically for just two negations. Most of the time you will just do it and not be affected. But with other things, just because you see an easy step, don't right away do it. Because you're going to be wasting time going through and then it won't make sense. So first, in your head, think it through. Will this take me anywhere? Or the best way is there anything else I could do? If there's something else I could do, consider it first. Then do the easiest step. So here, I can't think of anything. So I'm going to do it. So here, we're going to say not P or Q. Or not P and Q. Which is, I just kept it the same, except I negation. Okay? Now here is where a lot of people get stuck. Don't forget, this is not all there is to it. Like there's a lot of things that make sense that are not listed here. For example, this is where we'll actually walk into it. He found a way to do it using only the table, but you don't have to do it using only the table. You can do it using common sense. For example, here, what am I saying? I'm saying not P or Q. Okay, so I said let's do a quick truth table. like a small truth table. Let's say I make P true. So here we're going to say P equals true. That is a horrible T. Okay, P equals true. Now what will this do? For the first one, this will be false. Let's assume actually Q is also true, just for the plot, according to Mr. Abbey. Okay, so not P turns false, so this becomes false here. This becomes true. So this whole thing will return true. Or not P, which is false, and Q, which is true, but this is an and, so it doesn't really matter. Because this is an or, this already returned true. Okay? Now, let's turn P into, actually let's turn Q into false. And let's go with P true, and then we'll do P at false and Q at also false. So I feel like maybe that will get the idea across a little bit better. So if this is false and this is false, the true here will make this false, right? So this whole thing returns false, and it will make this false, returning false. Okay? Now, what if I made it true for the second scenario? So this is true, or this, let's say, right, it's false. This right away just returned true. So I don't even care what this is, because this already returned true. Okay? Now, let's make Q true like we did before. And as you can see, this already returned true, because I don't even care what this is, because Q is true here. This or made this whole thing return true. And this or made this whole thing return true because of this. So as you can see, like, I'm not even paying attention to this side. If not P is false, this will make the whole statement true. And if Q is false, and this is, sorry, what was it? I lost my idea. If this is false, it will make the whole thing true. And if this is true, and this is also true, it will make the whole thing true. I'm hoping like I'm getting the idea across. This doesn't matter is what I'm trying to say, because this is what's determining all these solutions. Like, as you can see, we never really need to check this. And this is called disjunction, which is, I don't believe it's here, which is not, yeah. So disjunction basically says some things don't matter. And in our case, this doesn't matter. And so not P or Q, disjunction. That would be your answer, and this is valid math. And so if he accepts it or not, I don't know, but this is definitely valid. Like, you could say, since we only depend on P to make the whole statement true, and if P is true, then we depend on Q to make the whole thing true. Therefore, we only care about P and Q, and we don't care about any of the other statements. And so that's the point for this part. He made it very long for some reason. Or I guess maybe because his was easier to understand, like if you're using the table, but it's lengthy. An important logical equivalence involving conditionals. This one, they just have the same truth table, so just remember, if you have this, you can convert it into this. That's basically what they're trying to say. It's the same truth table. Contrapositive is also equivalent. So if you take this here, and you take this here, and you negate both, it's equivalent to the original one. But do not forget that P and Q is not equivalent to not P or not Q. And P to Q is not equivalent to to Q then P. Like these don't equal the same. They only equal the same if you both, so you see here I flipped it. This came here and this came here. Okay, and here I didn't flip it, but I negated it. These are not the same. You have to flip and negate for them to be equivalent, and that's contrapositive. Now a lot of people when they see this, they're like, "Oh my God, I can't prove this." And this is actually one of the easiest ones to understand, or the easiest ones to prove. Okay, so two rules that you have to know. 2k is an even. Is even. Okay, why is that? Because any number times 2 is even. So whatever k is, if k was 500, 3, 6, 2, it will always be even if you multiply by 2, right? 3 times 2 is 6. If you take 9 and times it by 2 is 18. So that's also even. So anything times 2 is even. Now, any even number plus 1 is odd. So if I do 18 plus 1, that's 19 odd, right? 3 plus 1, well, that's actually odd. But 2 plus 1, so 2 is even, plus 1, 3 is odd, right? So if I do 2k, remember I said this is even. So if I take any even and add 1 to it, is odd, right? It just makes sense. That's all you need to know, really. So when they tell you to prove this, right, then what I'm saying is, okay, if whatever the fuck this is an odd integer, then n is an even integer. Now, the thing is, it's harder to go from this to this. Okay? So we want it the other way. We want to go from here to this part. But you can't, remember what I said up here? I said, so this is implying. Remember, this is if, then. So this whole thing is P, and this whole thing is Q, right? So what I'm saying is I'm saying P implies Q. But if I do it the other way, what am I doing? I'm doing Q implies P. And up here we said just switching them does not make them the same. You have to also negate to make them the same. So what I can do after removing all this gibberish, and I hope you guys are understanding what's going on, if I turn this around, if I say if n is an odd integer. Now, why did I choose odd? Because remember, I'm negating it. Because you have to not only flip, right? Not only flip, but you also have to negate for them to be equivalent. Okay? So if I do that, because remember, it's easier to prove this into this than the other way around. Okay? So if I do if n is an odd, aka negating my q, then 2 n squared, n squared plus 2n minus 1 is even. And you see, it's odd, but I negated it, so I made it even. Now this is equivalent. These two are equivalent, okay? These two are equivalent to each other. Now let's prove this. Well, since I said n is odd, therefore n, assume, so we're going to assume n equals 2k plus 1. Because remember, I said odd, so I'm going to make it odd. So let's assume this is odd. Then I want to assume this is even. So then n squared plus 2n minus 1 is even. All right, it's simple enough. Haven't really changed much. Now, remember, if n equals this, what happens if I take this and sub it in here? What will happen? That's really what I'm going to do. I'm going to take it, sub it in. So 2k plus 1 squared plus 2 times 2k plus 1, right? And then plus 1. Okay, so let's just, simplify it. Here, I'll do this to the side. So I have 2k plus 1 times 2k plus 1. So what will happen, you do this, right? So this is 4k squared, and then plus 2k plus 2k plus 1. Now you simplify this, it becomes 4k squared plus 4k plus 1. All right, so this will become that. 4k squared plus 4k plus 1 plus, distribute this in, 4k plus 2 plus 1. Now we're just going to collect like terms. So 4k, like I'm not doing any special math here, right? 4k plus 4k plus 8k, right? And then plus 1, wait, where am I? So I did this, now 1 plus 2 is 3, plus 1 is 4. Okay, now just looking at this, we don't know if this is odd and even, right? Like, how would you know if this is odd or even? The easiest thing you can do, remember what we said, anything times 2 is even. Can we make this times 2? What if I pull out a 2? Like, what if I just pull out a 2? So divide this by 2, divide this by 2, divide this by 2. You know, I'm going to pull out a 2. So what will happen is pull out a 2, this becomes 2k squared, plus this will become 4k plus 2. So now, like, this looks ugly. I'm not going to try to figure out if this is odd or even. So I don't care what this is. This could be odd or even. But since I'm multiplying it by 2, this will always be even. Right? Just like we said here. It doesn't matter what k is. This will always be even. Therefore, I just proved, remember what I said? If n is odd, which we made it, here, let me change the color. If n is odd, and I made it odd, right? Then this is even. And we just proved it's even because it's multiplying by 2. And so, and since this, let's choose green, since this part right here, right, us negating and flipping is equivalent to this part, us proving this is the same as us proving that. Okay? So this is honestly, literally, whenever you see some question anywhere near to this is exactly how you do it. It's always the same way. Now, not always do you flip, because sometimes it's already flipped for you. So that's really how you always do it. Now here, they want us to prove this. Remember, up here what we said. We said P then Q is equivalent to not the first one. So don't remember it as not P. Remember it as not the implier, I guess. Whatever you want to call it. I'm not sure what this portion of the if then is called. I just know P implies Q. But what you just want to remember is you're noting whatever is here. Whether that's a whole statement, whether that's Q, or, it doesn't matter. You want to negate the whole thing. Okay? Then you just do or, whatever is the then part. Okay? So now when we go here, remember, I have this or this. Like I could name this R and S. Like R implies S. So if I want to prove this, first I gotta, like, I can't do anything with this. So I'm gonna convert it into this logic up here. Okay? So remember, R, S converts to not R or S. So I'm gonna not R. What's R? R is not Q, so it becomes not Q. Oops. Or not P. Now we can just simplify. So then we have not and not. This cancels out. It just becomes Q or not P. Right? Now once I've done that, I can just not P. I'm just switching them around, which is fine. And as you can see, I went straight to this. We just proved it. Okay? Thinking an implication as converse are logically equivalent, but yeah, remember, this, when you flip these, they're not the same. Okay? And when you don't flip them and you only negate, they're also not the same. You have to flip and negate. So if you take the converse, and you also apply the inverse to that converse, then it becomes technically the original or equivalent to the original. All right. Now here the questions are all truth tables. Determine whether this is a tautology. So all you got to do is use a truth table and make sure it's always a tautology. Now one thing you could do is probably simplify it, but it would be easier to do a table for this than simplifying it. If you do want to practice, do try to simplify it. And then if you simplify it to just T, then that means it's a tautology. So show that these are not logically equivalent. Again, truth table, all these are truth tables. So you don't gotta worry about that. Use truth table. These are the homework questions. Use truth table. We did all these in last lecture. That's why I'm not doing them. We also did this, which is negate of each of the following statement. So when you get this, Jane is rich and happy, it becomes Jane is not rich and not happy. Like Carlos will bicycle or run tomorrow. Carlos will not bicycle or run tomorrow. Or will not run tomorrow. So that each of these conditional statements is a tautology by using truth tables. Again, more truth tables. Determine is a tautology. Each exercise show that two compound propositions are logically equivalent. Either show that both sides are true or that both sides are false for the exactly same combination. So this is truth table. Show that this and this are not logically equivalent. Again, truth table. So this is lecture 2. I hope you guys learned something. Hopefully I'll be able to cover most of the lectures for tomorrow's test today, but I'm not sure how realistic that is. So I'll keep you guys updated and have a good day. Where can I end this? Hello.